Okay, so last time we discussed Tutt's theorem. So I'll just give you a brief recap of the theorem because many of you had doubts. So okay, so what is Tutt's theorem? Is it visible?
Yes, it is visible.
Okay, it seems very faded, this pen.
A bit faded, but it can be seen.
Okay. Okay, so what Tutt's theorem says? It says that given a graph G, it has one factor if and only if G has one factor if and only if Qg minus S is at most cardinality of S for all subsets of vertex set. Okay, so theorem says that number of odd components in G minus S is at most cardinality of S for any subset of V. Okay, so what was the proof? Forward direction, this is easy. In forward direction, what we saw that okay, it say it has one factor, then every vertex subset should satisfy this condition. Say if you have some subset S which fails this condition, then what happens? So if you have some set, if there is some S such that Qg minus S is strictly greater than cardinality of S, then what happens? So you have this S set. This is very faded. Okay, so we have this set S, and we are saying that okay, we have these number of components. These are odd components. Okay. So if I have for any odd component, if I want to have a perfect matching, I cannot match everybody inside the component, right, because its size is odd. So there must be at least one vertex is matched outside this component, right, and where it can match? It can match only in S, right, because all the components are connected by S. S is the separator of these components, right. So these one vertex is at least one vertex from every odd component is matched from the set S, right. So now if number of odd components is more than the cardinality of S, then what does it imply? That at least one odd component will be remained that such that you cannot match any vertex from this odd component to S. So because so I can match like this, but because the cardinality of S is strictly less than the number of odd components, so some odd component will be left with some unmatched vertex. Okay. So that is why it is not true. So that's contradiction for one factor. So let's look at the other side. Okay. So we got some contradiction here. So for reverse side, we will prove the counterpositive statement. So we have that graph has no one factor. So we want to show that there is some set which fails this condition. Okay. We call such set which fails Tutt's condition, we say that okay, it is bad set, it is bad for us. So that's what we said. So our goal is, so we are assuming that G has no one factor, and our goal is to find a bad set. Okay. So what we said last time, So, among all those graphs which fail Stutz condition, we will choose that graph which has maximum number of edges. Okay. So, a maximal edge graph which fails Stutz condition. What does it mean? So, say H is edge maximal graph which fails Stutz condition. What does it mean? That in this set H, this is edge maximal. So, if I will add one more edge into this H, then there will be one factor. Every every subset of vertex set satisfies the Stutz condition. So, that is H. Okay. Now, in such H, we want to look at how your some bad set or some set would look like. So, you have some set S, S is a vertex subset, and you have these components.
Is it possible you can take a minimal edge maximal graph, because usually when we
Minimal?
yeah, because when we prove such theorem,
But
we usually take the smallest graph and say that if
which satisfies the condition. Here we want to fail the condition. So, we are in the counterpositive, right. So, we want to fail some condition. We are saying okay, because eventually if you have all possible edges in complete graph, so if it has even order, then you can find a perfect matching, right. So, you cannot like arbitrarily add and you will still not get one factor. At some point your set which was failing Stutz condition may start to no, actually it is like it is not exactly the same set, but you can modify the sets so that it satisfies Stutz condition, like after adding some edges. So, if you have all possible edges, then it is like if it is odd, graph is odd itself, then only you will fail one factor, otherwise you have one factor, right.
no, my question was that while proving, so usually when we prove that okay, this will not hold, so we always prefer to take the minimal graph and say that oh, on minimal graph it fails, then look, it fails on the any graph you take. So why do we have specifically take edge maximal graph here?
So, you are saying that we take minimal and we say that okay,
Usually
for
I am saying.
yeah, usually that on minimal graph it fails. So, on our original graph also it fails, like
Or
G
any
also,
graph which is
that also fails. Okay. Yeah, so that's the point. लेकिन हमें क्या चाहिए? Like we are assuming that on our graph it fails. Now I want some graph that like when it won't fail. So I'm saying by adding edges, there will be some point when it won't fail. Because even for even order, if you see, you may not have a one factor, right? Even order graph also. In that case, but if you add all possible edges, you will have a one factor. Even one like Hamiltonian cycle is enough to match all the vertices, right. So, I just can add those edges, but in this, so that is why here we are failing and we want to say okay, we will just increase the edges up to that point when it starts like now holding the condition instead of failing. So, that is why in this case we are just looking at maximum. It depends on the context actually. So, here for us, like because we know by adding the edges, like we may come to a point where the sets starting holding the condition. Okay, so now for in this graph, we said okay, we have some subset S of V and these are components, then how the graph will look like. So, what we said here? So, we said here that okay, this set satisfies two conditions. One is that every S in S for every S in S, S is adjacent with every other vertex in the graph. And second condition is that every component is complete. So, every component is G minus S is complete. Okay. So, we say that okay, in edge maximal graph a set S of vertex set satisfies these two conditions, and if we find a set such that, then we will say that okay, I can find a bad set. Okay. So, I want to like characterize my bad set by this property. So, I will say okay, if I am able to find some set which satisfies these property, then I have a bad set. And what is the bad set in the case? So, either so there will be two cases, either S is bad. If S is bad, then we are good. We wanted to find like we were looking for some bad set and S is that bad set, or if not, then what happens? If not, if it is not bad, that means Q G minus S is at most cardinality of S. And now, because you know that the number of odd components is at most cardinality of S, you can match the one remaining vertex from each odd component from the set S, right. So, we can match one extra vertex here like this, because S cardinality is at most Qg minus S, at least Qg minus S. Okay. And because this is a clique by stars property and every component is a clique, so we can match all other vertices inside the component and inside the S also. But now, because we started by assuming that G has no one factor, that means I should not be able to match everybody. So, in these component I can match, because these were like with odd order and one vertex I have matched from S. So, remaining are like clique having even vertices, so I can match. So, the only problem may be that the remaining vertices in S which are unmatched, the number of vertices is odd. Okay. That could be the reason that we are not able to match. So, in that case, what is the cardinality of whole graph G order? It would be odd, right, because now, so if you count the number of vertices in every component and together with these matched vertices of S, this is even, and the remaining vertices in S is odd. So, in this case cardinality of G is odd, and so we can assume that your phi empty set is your bad set, because empty set in G minus S, like you have one big odd component, and so this condition fails. Okay. So, that means if I have some set which satisfies this star property, then we are done, because we can return one of these are bad set. So, our goal is to find a set S satisfies star. Okay. So, now we said in this edge maximal graph, this S has the property that every one is like each vertex is adjacent with every other vertex, right. So, we will start from there. We will say okay, let S be the set of all those vertices such that UV is an edge for all U belongs to V, okay, and U is not equal to, or we don't have to write also because there is no loop. Okay, so yeah, so this is my set. I am taking the set S as the set of vertices which are adjacent to everybody else in the graph. So this is my set S. Now, so either S is bad or not bad. So we have two cases. In case 1, if S is bad, then we are done, right? We found some, yeah. So either S is bad itself, then we are done, or S is not bad. No. Actually, we want, for this set, we wanted to find a set which satisfies star. Now I have defined some set. Now I want to see that it satisfies star or not. So first condition, it satisfies, right? We started with such set. So first it holds. Now if second also it holds, then we are done. Okay. So S holds star first. If S holds star second condition, then we are done, because then S is the required set. So now if not, okay. So that means S doesn't hold second property. So that means there is some component which is not complete, okay. So it implies that there is some component C in G minus S such that C is not complete. Okay. So I found some component which is not complete. What does it mean? That there exists some pair such that A prime is not an edge. Okay. So if A prime is not an edge, then look at some path, because this is a component. So there is some path between A and A prime. So let P be a shortest path. So P is a shortest path. Okay. So this is my shortest path. Okay. So now AC is not an edge in the component in the graph, because this is shortest path, right? So because P is shortest, so AC is not an edge. Now look at the vertex B. For B also I want to find some non-neighbor. So can I find some non-neighbor for B? Last time you had questions about this. For B, now can you find some non-neighbor, right? Because since B is not in S, so there exists some D in B such that BD is not an edge. Okay. Because of this definition of S. So if there is a known neighbor of B, that means B is adjacent with everyone. So B should have been in the set S, right? So that means B, there is some vertex which is not adjacent with B. This is not in S because. Okay. So we found two non-edges. So now what we'll do? So, we started with some edge maximal graph. So, now if you add any edge to edge, then that holds Tutt's condition, and so it has one factor. Okay. So, because of the choice of H plus AC and H plus BD has one factor. It's okay. So, both has one factor. So, say this is M1. So, M1 is a perfect matching in H plus AC and M2 is a perfect matching in H plus BD. If there is any doubt, please ask. I am going speedily because we discussed this last time. I just want to give you a recap. Like, okay, so we found these two perfect matching in these graphs, H plus AC and H plus BD. Okay. So, now look at some path. So, by these perfect matching, we are saying that these are perfect matchings in H plus AC and H plus BD, but somehow we want to find some odd cycle. So, the idea was that we wanted to come up with some odd cycle which has alternated edges from M1, M2, sorry, even cycle from M1 and having alternated edges M1 and M2, and it contains some this edge BD, and so that if we remove this BD edge, then also in the remaining graph we can give you a perfect matching we can construct. Okay, that was the idea. So, that is how we want to come up with contradiction. Okay. So, let us starts with some path, maximal path. So, let P be a maximal alternating path with edges from M1 and M2, and also it starts with D, and it starts with D, that is important. Okay, and we are looking for this path in H. Okay. So, P is equal to D, and you have something V1, V2, V3. So, these are edges. Okay. And you have last vertex some V of this path. Okay. So, this is alternating path, right. So, what can you say about the first edge of the path, where it will be? M1, right. So, this is from M1. Why? Because this is an original graph H. So, M1 was a matching which saturates every vertex and AC. So, in original graph H, AC is not there, AC edge is not there, and BD edge is not there, but still M1 saturates every other vertex other than A and C. Okay. Similarly, M2 saturates every vertex other than B and D in my graph H. Okay. So, because BD is not there in H, so D, if D is saturated by somebody, it would be M1, right, M1 matching. So, that is why first edge. It is from M1 because I am taking this path in my graph H, So, M2 saturates every vertex in H plus BD. So, that means in original graph H, it does not saturate B or D, B and D both. Okay. So, only B and D are not saturated by M2, and by M1, similarly by M1, A and C are not saturated. So, now this D is saturated by M1 only, right, it cannot be saturated by M2 in H. So, that is why first edge is from M 1, then M 2, then M 1. So, now the question is that what about the last edge, where it belongs. So, that is why we have two cases. So, case 1, say last edge belongs to say M 2. I'll take M 1 first. Okay, so say last edge belongs to M 1. So, what will happen?
With one more condition, and it start with D and start with H from M1. Then it's fine.
If you are starting with D, then first edge will be from M 1.
Why? I can take FBD.
Because I am taking the path in H. So, D is not saturated by M 2. So, if you are starting a path, then it would be M 1 edge. So, first case is when last edge belongs to M 1. If last edge belongs to M 1, what can you say about V? So, in M 1 what we said that M 1 saturates in H, M 1 saturates everybody except A and C. In M 2, M 2 saturates everybody except B and D. So, if last edge is in M 1, what does it mean? And this is a maximal path, right. So, there is no edge from M 2 now incident on V. So, that means V is not M 2 saturated. V is not M 2 saturated. What does it mean? B, right, because M 2 saturates everybody except D and B. So, if last vertex is not M 2 saturated, then it must be B, right, because D is there. So, V is, in this case V is B. Okay. So, if V is B, then in H plus BD graph we have this edge, right. So, in H plus BD we have this edge. So, what we found? A cycle, and what is the length of this cycle? This is B, this is D. What is the length of this path? Path is odd, but if cycle is even. So, in H plus BD we found a cycle C, in fact an even cycle C, and BD belongs to C. Okay, that is what we got. Now, in second case, if last edge belongs to M 2. Okay. So, last edge belongs to M 2. So, this is M 2. So, if last edge belongs to M 2 and you cannot extend the path, this is maximal path, what does it mean? It means that V is not M 1 saturated. If V is not M 1 saturated, then what is the choice of V? A or C, right? Because M 1 saturate everybody else except A and C. Can you please mute yourself, Sashikant? I think.
Sorry.
Oh, that's okay. Okay, so if last edge belongs to M 2, that means V is not M 1 saturated, and so V is either A or C, because only these two vertices are not M 1 saturated. So, this is either A or C. So, you take A or C any one, because both of them are adjacent with B, right. So, A is adjacent with B. So, we have this B here, and
Why you take that B?
because I wanted to find some, my goal is to find even cycle. Okay. So, now I know that V is A or C, then both of them are like adjacent to B. So, I have this edge AB and I am adding BD. So, in H plus BD again I found some even cycle. So, same in H plus BD we found some this same cycle C, which contains the edge BD. Okay, so, in both cases we found this. So, now we come to the end. What we want to say that in H plus BD we found some even cycle. So, if you remove BD from H, then can you give me some matching, some new matching which saturates every vertex of the cycle by removing B and D? So, that is the question. Okay, so let us look at the second case first, because from here we can see. So, in second case, I am saying M2 saturates every vertex except B and D, right. So, I want to define a new matching. So, take all the edges. So, from the cycle C, remove all the M2 edges and take union with H the whole M2 minus C, okay, or set minus I like that. Okay. So, this is I am defining a new matching. So, a new matching is that from the cycle, in both the cases, from the cycle I am removing M2 edges and adding all other edges into my matching, and outside this cycle whatever was saturating, like take the same matching. So, outside the cycle, so outside this cycle C we had a perfect matching for the remaining graph, right, from M2. So, I am taking the same edges, same set of edges. Okay. So, my claim is that this matching is perfect matching in H.
I have one question. Like, why we are finding this cycle? Like, if we just find the path, we just swap the edges. What is the problem?
Yeah, that also you can do, but
The edge AB or CB, this doesn't belong to any of the matching. So
yeah,
it's basically
yeah,
like augmenting the
yeah, that is correct.
Before case
That is correct. This is just for like simplicity, like H plus BD. In H plus BD we found some cycle where we are just having edge BD and we were saturating edges. Yeah, it is same actually. We are not here also, we are just removing BD, and in the remaining path only we are just find some matching which saturates every vertex. So, yeah, this is same. So, you can say that way also. So, in both the cases you can do, right. So, in this second case, I am saying remove M2 edges, and every edge which is not in M2 in this path, make it in the new matching. So, now all the edges of M1 are in matching, and this edge AB is also in the matching. So, that means it saturates every vertex, B and D also, it saturates B and D as well. And in first case, our last edge was from M1, and so it was this vertex V itself was B, and so we had this first edge and last edge both are in M1, that means you have M2 augmenting path with respect to M2, because first and last vertex was M2 unsaturated. Okay, so in both the cases you can augment. Okay.
One question. The first case, could you please tell how A is saturated?
If in first case this vertex,
Second case, sorry.
okay, in second case we said that this is A and this is B. So every edge which is not in M2, we make them we put them in our new matching. So all the M1 edges are, this last is also M1. So all the M1 edges and this edge also. So I am not talking about where it was earlier, M1 or M2, but I am saying that now I can put in my new matching M prime, right? I can put, huh?
B is M1
No, we don't know, because if you put this in M1, then A is also M1 saturated, right?
A is not M1 saturated because H plus AC has.
It should not be, but if you put this edge in M2 in M1, then you are saturating A, right? So A is not saturated by M1 in H. So that's why it cannot be in M1 actually. So, but yeah, B must be M1 saturated. So maybe there is some edge like this with from some other vertex. But we are just looking at this path. You are saying, okay, this edge was not in M1, not in M2, but now I just want to put this in my new matching M prime in both the cases. Any doubts? Anyone? Okay. So in our next theorem, so this theorem said that okay, for every set, number of odd component G minus S should be at most S, okay, for every set. Now we want to look some more detail of the structure of some set. So next theorem characterize this one factor with some existence of some set which has very special property, okay, and which gives you some more structure. Okay. So first let's define this graph GS. So given some set S, you have these components. Say, so S is a subset of V, and let CG minus S is the set of all components in G minus S, okay. Okay, so what I want to define this set, this graph, new graph GS. So in GS, what I'm doing, this set S is there, we have some edges like this. These are components in CG minus S. So I am saying that, okay, let's remove all the edges from the S and remove all the edges from, not remove, but actually we are contracting each component into a single vertex, okay. So basically we want to see that whether we able to match the odd components with the set S, okay. That's what we were doing there also, like that was the idea of behind that bound, right, that any odd component should be matched with some vertex in S, right. So, so we are saying that okay, let's forget about the edges inside S. So, GS comes with 2 operations. So, first is, I will just write it. First is that remove the edges inside S, and the second operation is that contract each component into a single vertex. Contract each component in CG minus S single vertex. Now, the we'll say that S is matchable to CG minus S if we can find a matching which saturates S. Okay. So, this is the definition. We are saying that now these have contracted as C1, these are my components C2, Ci, and I am saying that I want to you have some edges like this. So, this is a bipartite graph, right. So, GS is a bipartite graph defined, and we are saying that S is matchable to CG minus S if there exists a matching saturating S in bipartite graph GS. Okay. So, we say that S is matchable to the components if there exists a matching which saturates the entire set S. Okay. So, this is a matchable definition, first definition, and there is one more definition we require, that is one factor critical graph. So, a graph is one factor critical. Graph G is one factor critical if G has no one factor, but for any vertex V in VG, G minus V has a one factor. Okay. So, a graph is called one factor critical if G has no one factor, but if I remove any vertex from the graph, then the remaining graph has one factor. Okay. So, basically this one factor critical graph, what is the cardinality? Odd. So, basically this has odd cardinality. Okay. So, the state, can I give here? So, my theorem statement is that is it yes, odd cycle. Odd cycle is one factor critical. Every graph G has a set S which satisfies So, every graph has some set S which satisfies the following properties. First property is that S is matchable to C g minus S, and second property says that S is matchable to C g minus S and every component in G minus S is one factor critical. With respect to S. So, first we have this set S, and then we are just in G minus S we are contracting each component, and in S we are just removing the edges from S, keeping all the vertices.
So it's important to mention S with respect to which?
From a particular set S. So, this is corresponding to set S, that is why S is in the subscript. Okay, so, this is set dependent, we are just talking about this particular set S. Okay. So, this theorem says that every graph G has a set of vertices which satisfy these two conditions: S is matchable to C g minus S and every component in G minus S is one factor critical. Okay. So, yeah, you can have multi edges.
So we retain the multi-edges.
Yes, yes, we retain the multi edges. Or we can remove also. Basically, we want to just saturate all the vertices in S. So, you will saturate only by one of the edges, right? So, yeah, we can just remove also. We will use anyway one edge. And also like Hall's condition also satisfy for multi graph also with multi edges. So, that is okay. Okay, so first property says that S is matchable to C g minus S. So, what does it imply? First condition, that S is matchable to C g minus S, that there exists some matching in this GS bipartite graph which saturates every vertex in S. Okay. So, what does it mean? That what can you say about the cardinality of S and cardinality of C g minus S? Look at this bipartite graph. So, in this bipartite graph, I am saying that S is matchable to C g minus S. What does it mean? This is less than equal to, right? So, this is less than equal to, because S is matchable. So, for there exists some matching which saturates all the vertices in S. So, cardinality of S cannot be more than cardinality of C g minus S, right. So, this is not the complete theorem. Theorem says that if given such a set S, we can characterize the one factor. Okay. So, given such a set S, G has a one factor if and only if cardinality of S is same as cardinality of C g minus S. Okay. So, this is the theorem. This is the characterization, that if we able to find some such set, if every graph, first of all every graph contains such a set which has these two properties, that S is matchable to C g minus S and every component in G minus S is one factor critical. Okay. And the second statement is that given such a set S, G has one factor if and only if the cardinality of S is exactly same as the cardinality of C G minus S. So, one way is there, from the first property it holds. So, the only thing you need to show is cardinality of S is at least C G minus S basically. Okay. So, this is the characterization. Okay. So, these are the two parts. What? Given
Why such a factorization of set S actually, that it has a one factor if only a cardinality S is equal to Cg minus S.
yeah, we will prove that.
Okay.
So, this theorem has two statements, two parts. One part is that the existence of such a set S, and in the second part, if you have such set S, then can you say this, the last statement, that G has one factor if and only if cardinality of S is same as C G minus S. Okay. So, let us look at the second part first, because this is easier. So, okay. So, suppose you have such set S which satisfies these 1 and 2 properties. Now, if G has a one factor, okay, so if G has one factor, okay, so just to simplify it, so first look at the, because we have given this, we have now this set S which satisfy these two property. So, let us first look at the these two properties, what does it imply? So, first property implies that cardinality of S is at most cardinality of C G minus S. What about second property? Second property says that every component in G minus S is one factor critical.
We have one component in each, one vertex in each component that is unmatched.
That is unmatched. So,
Exactly one component.
exactly.
Only one vertex.
For every component you have some vertex which is unmatched. What does it mean? That every cardinality of every component is odd, right? So, second property implies that every component in G minus S is odd component. Okay. That means this is number of odd components, right? The cardinality of C G minus S is exactly the number of odd components, because every component is odd. So, that means cardinality of S is at most Q G minus S. Is it correct? Right? Okay. So, at most this. Now, we are in the forward direction. We say that okay, G has one factor and we want to show that they have same cardinality. So, G has one factor. So, we have already seen one characterization for general graph having one factor. So, what is that?
It's the opposite.
We saw this Tutt's theorem,
Right?
right?
Minus S is upper bounded by cardinality of
Odd
S for
components.
Yes.
Odd components, right, by Tutt's theorem. So, because G has one factor, that means every subset satisfies Tutt's condition. So, this set also satisfies Tutt's condition. That means G has a factor. So, by Tutt's condition for this set S, cardinality of S is at most Q G minus S, right. So, by given these two, what we got is cardinality of S is Q G minus S, which is same as the cardinality of C G minus S. Done? Is it okay? Okay. So, what about reverse? For reverse direction, what we have, that cardinality of S is cardinality of C G minus S, and we want to show that G has one factor. like let's look at this set S, which is with us. So what properties S has? That S is matchable to Cg minus S, right? That means there exists some matching which saturates every vertex in S. Okay. And because cardinality of S is Cg minus S exactly, so to saturate every vertex in S, we have to take one edge to one component, right. So, that means it will look like this, and this is the entire set S. Okay. And what's the second property? Second property is that every component in G minus S is one factor critical. What does it mean?
If we remove the
Yes.
if we remove the matched vertex in every component, so that component becomes a perfect matching.
Yes. So, if we remove this vertex from these components, then they has one factor. So, you have some matching which saturates everyone here, okay, and all the vertices of S are matched with one vertex from Cg minus S. So, this is one factor for G, right. We have covered every vertex, we have saturated every vertex. So, we can just simply give one factor. Okay. So, we give one factor like this. Okay. I am not writing the details because it is already late. Okay. So, it is clear, but right, that we can give one factor. We can give one factor, so we are done. So, this second part of the theorem we are done, we have done with the characterization. Now, we have to show the existence of such set S. Okay. So, now our goal is to show the existence of such set S. Okay. Okay. So, what we have, so let's define some measure. We will see that any subset of vertex set, how, so okay, maybe some sets are failing Tutt's condition. Okay. So, we want to see that okay, any set, any subset of vertex set, how badly it fails Tutt's condition. And badly fails means how do we measure that? By measuring the difference. So, we are saying that okay, some set is like failing Tutt's condition, that means cardinality of S is strictly less than Qg minus S. So, we are defining the measure that how badly some set is like failing Tutt's condition, we define by the measure dt, and we say that this is Qg minus T minus cardinality of T. Okay. So, I am defining this measure for T. Okay. So, let's take a family of all the sets, all the vertex subsets of V, such that this this measure is maximum for these graphs. So, basically we are just for every subset we are just looking at this measure, that Qg minus T minus cardinality of T, and among all those sets I am just taking the subsets which has maximum measure. So, which are failing the touch condition, you know, worstly. Okay. So, these are the worst sets. So, I am taking the family of all those sets where this measure is dt is maximum. Okay. And now, from this family I am choosing one set which has largest cardinality. Okay. So, let S be some set from the family F such that cardinality of S is maximum. So, basically for this we want to find such a set S which satisfy these conditions. For this set I am just taking a candidate from this family which fails touch condition very badly, okay, like the worst.
Why you take t, will you explain that t, define t, dt that?
dt is, we are defining the measure that how badly this set T is failing the condition, because if this T is failing the condition, that means Qg minus T is strictly greater than T. Okay. So, I am just taking the collection of all those sets which is where dt is maximum. So, maybe because we are finding this for every T, so maybe there are sets which satisfies whole touch condition. So, in that case it would be negative, but it is okay. I am just looking at the maximum one. Okay. And what if touch condition hold for every subset?
Maximum or positive?
Maximum.
Maximum means what? Like
Maximum number, cardinality, this is a number, right? This dt is a measure, this is a number.
that will be 1t.
Hmm?
I mean, it won't be a family of sets.
But that one number can be achieved by many sets, right? Maybe for one subset dt is 2, but for other subset also dt is 2,
But
ds
there
is
might
2.
be like another subset T prime which has a positive dt value, but
I am saying the maximum one, whatever be the maximum among all the dt's, all the subset, I am picking the maximum one, maximum value of dt, and then I am making this family for all those subsets which achieves this dt, which has this dt value.
this is basically not a collection of all those subsets that fail touch condition, but instead only like those that achieve maximum value.
Yeah, which achieves maximum value. This is not for every one, like, no. I am saying which is like failing the condition equally badly and like worst among the whole sets, all the sets. Okay, and I am picking the maximum cardinality S, that we can do, right? Among all those sets, I am picking the maximum cardinality set. So, now I am saying that this is my candidate which satisfies these property we want to show. Okay. Okay. So, now our goal is to show that S satisfies this condition and this condition. And one more thing. So, for this ds, what can we say about ds? Okay, one second.
Let S belongs to family such that S is maximum, that you don't need just. Like S is already maximum because this family contains only maximum.
Here we are saying ds is maximum, here we are saying cardinality is maximum. So, we are saying ds is also maximum, but we are among all those sets also we are just picking with maximum cardinality set. Okay. Now, we want to show that this set satisfies these two conditions, first and second. Okay. So, let us first to show S is matchable to Cg minus S. Okay. So, S is matchable to Cg minus S, we want to show. Suppose S is not matchable. So, that means in that bipartite graph GS, we do not have a matching which saturates S. So, what can we do? If we are assuming that S is not matchable to Cg minus S, then what do we have? We have seen so many theorems, right? And for bipartite graphs, Hall's condition, right? So, for bipartite graph, we give a characterization by Hall's condition. So, let us use that. So, let S is not matchable. Okay. Let S is not matchable. That means by Hall's condition, there exists some subset of S such that cardinality of S prime is strictly greater than the cardinality of neighborhood of S prime. Okay. So, let us look at the graph, what is going on here. So, we have this set S, we have this Cg minus components in Cg minus S. We are saying that there exists some subset of S, S prime, such that, okay. So, let us look at the graph G minus GS. Let us look at this bipartite graph GS. Now, so in GS we do not have components, we have we have vertices corresponding to each component, okay, like this. So, we have some whatever. Okay. So, what we are saying that for this set S prime cardinality is strictly greater than cardinality of neighborhood of S prime. So, it has some neighborhood. What does it mean? It sees some of the components. So, say it sees S prime sees these components. Okay. So, let us define some new T. We say that, okay, this from this set S, let us remove this S prime and then check whether like what is the measure of the remaining set. Okay. So, we are saying that, okay, let us remove this subset S prime from this S and now look at the measure of this, whether it fails Stutz condition or not, and like how badly it fails. Okay, so, for now dt, what is dt? dt is basically q g minus t minus cardinality of t. q g minus t means number of odd components in g minus t graph. So, now my t is this set, right, this portion. Now, notice that every other component other than this is adjacent to this faded region only, that means T. So, number of odd components in G minus T, how many it would be? So, let us look in the comparison of odd components in G minus S. So, for odd components in G minus S, we knew that Q G minus S odd components were there earlier. Now, what is Q G minus T? So, earlier total odd components were Q G minus S. Now, because I have like pushed this S prime here, so like it has covered some of the odd components, right, some of the odd components. Now, those odd components I have to remove, from my Q G minus S, right. So, Q G minus T is Q G minus S minus number of odd components covered by S prime. Is it okay? Oh, yeah. Yeah, covered by S prime or in NS prime, or number of odd components in NS prime, or you can say that. Okay, covered or in NS, same thing. Is it okay? This point? Okay, so we have removed some of the odd components which were earlier there. Now it is covered by S prime, or basically they are now in NS prime. Okay, and minus cardinality of T is cardinality of S minus cardinality of S prime. Right. Now, what is this number? How many odd components can be in NS prime? At most cardinality of S prime, right? So, at most cardinality of S prime. So, that means this is greater than Qg minus S, because we are subtracting, minus cardinality of S prime, and we had this minus cardinality of S plus cardinality of S prime. Okay. So, that means what we got, Qg minus S minus S. So, we got that, and this is d of S. So, what we got, dt is strictly greater than d of S. This is a contradiction, right, because we chose S with maximum dt value, right. So, this is which contradicts the choice of S. Now we are using, we are saying that S had the maximum value, dt value, ds value. But now we generated some other set T which has greater value, greater d value. So, this is a contradiction, right? We started with.
My question is that where have we used this fact that the cardinality of S is maximum?
Oh, okay. We have not used here. So, in this case only we have used that this thing, that ds is maximum.
So, all I'm concerned is it sufficient to take a set from this family, or we have to take a set which is of maximum cardinality?
Yeah, maximum cardinality. Like you can, it's okay. There is no harm to choose maximum cardinality set.
No, if maximum cardinality is used somewhere in the proof, then probably we want to have.
Yeah, so we'll see. We have just proved the first property yet. Okay. So, here we are done with the first property. So, S satisfies first property because of the contradiction. Okay. So, next, our next task is to show that every component in Cg minus S is to show that every component in G minus S is one factor critical. Okay. So, for one factor critical, what does it mean? Like one G, some component is one factor critical. So, what we have to show?
Remove any vertex
And it has one factor, right? So, but first of all it should have odd cardinality, right? So, every component should have odd cardinality. So, first we will prove that okay, every component is odd component in Cg minus S. Okay, so, that is our first task. So, first our goal is to prove Cg minus S, every component is Cg minus S is odd. Okay.
One doubt. So the S we are using in this second part of the argument, is it the same as we got from the first part?
Yes, yes,
Continuing.
yes. for the same set we want to prove both the condition, that S holds both the conditions. So now we are on the in the second condition, and first to prove that it is one factor critical. So let's prove that every component is an odd component. Okay. Okay. Suppose not. So you have some component. So let there is some C belongs to Cg minus S such that C is even. Okay. C is even component. We want to make it odd. So what can we do? We can just push one vertex into S, and we can make it odd, right? So what we have? We have this set S, and there is some component which is even. We are saying that every component is odd, but we want to prove that every component is odd. Suppose we have some even component. We want to make it odd. What we can do? We can just take one vertex and move to S2, move it to S, right? We can try to do that. So let's pick one vertex V and just shift it in the S. Then the remaining now part is odd.
But then S is matchable to G minus S.
Huh?
First condition is S is matchable, then how would you match S? Oh, that will be contradiction.
That's where we will get the contradiction, right? We are assuming that C is even. So basically we want to show that okay, C was already odd. So we'll get to some contradiction. Okay, so let's C is even. So what we do, we just let some vertex V belongs to C. Let the let's remove V from C. Okay. Now just picking one vertex from C and putting in S, this C component C itself, that may get disconnected, right? That may have you know, V might be some cut vertex there in the component. So when you put V in the set S, then you may just disconnect the set C. So one second, let's remove some part. So what I am saying is that okay, we have this set S, we have this component C. I have picked one vertex V and push this inside. Okay. Now this V may be a cut vertex inside C. So it may happen that when I am just removing V from this component, it is making new components, right? It may not be connected anymore. But even in that case, this will be connected to S somehow, right? So now maybe in this new portion we have some components in C minus V. Okay, so C minus V, and let's put this V inside S. So earlier the cardinality of C was even, right? Now I have removed V. That means the cardinality of vertex set of C is odd, right? So what does it mean? What can you say about the new components maybe? One of them is odd, right? Because the total number of vertices is odd. So one of them is odd. Okay. So this is one point to look at. And what we did, we removed V and we put this inside, we pushed this inside S. So this is my new set. Let's check the measure of this set. So D of T is Qg minus T minus cardinality of T. Now, Qg minus T is the number of odd components in G minus T, right. So, what is this number? We just argued now. This is no, it is this is the number of odd components. At least. So, we just argued that at least C will give you at least one of the new odd component, right. At least one of the odd component. We may have more than one odd components, but at least one odd component is there, right. Okay. So, earlier we had these components, this was one of the component and we had other components as well. These other components are still there, right, and this one where I have did something like this was even. So, this was not counted there. So, I am saying that all the odd components which were in G minus S are still there, right, and from this C, because this was even earlier, but now I have because pushed one vertex inside. So, its cardinality has become odd, and so it will give me at least one of the new odd component, right. So, that means this Qg minus T is at least number of odd components in S plus 1, right. And what is cardinality of T? This is cardinal minus 1. Okay. So, this is basically D of S. So, we found this new set T has measured at least D of S. But now, what is the cardinality of T? S plus 1 strictly greater than S. So, now we are using this fact that we picked a set with maximum cardinality. So, this contradicts the choice of S. Okay. So, that means we are done. We got some contradictions. So, every component is odd. Now, the last part is we want to show that now every component is odd, but it is one factor critical. That means, if I remove any vertex from any component, then it has one factor. We want to show that. Okay. So, let us write again rule to show. Okay. Okay, let us write to show every component in Cg minus S is one factor critical. Basically, for any C belongs to Cg minus S, C belong to Cg minus S, I want to show that for C minus V has one factor for any V belongs to C. So, basically we want to show that for any component in Cg minus S, C minus V has one factor for any V in C. Okay. So, let us again let us use contradiction. So, let us prove by contradiction. So, suppose G minus V has no one factor. Okay. So, let C minus V has no one factor. So, if C minus V has no one factor, then what can we do? What we have? Use some result, like we have results, right? Cg minus, but we don't know like it has one factor or not. This is one, if one factor is there, then we say that this is true. So, this part is this, like we don't know this, whether this is true or not. Huh? Yes, use struts condition, because we have one characterization, right? We have proved earlier. So, if C minus V has no one factor, what does it imply? That by Tutt's condition, there is some set which fails Tutt's condition, right? So, there exists some set, say S prime, which is a subset of C minus V. Let's say this, let's call this C prime. So, this, okay, there exists some set S prime, subset of C prime, such that Q, now our graph is not G, but this C prime, right? C prime minus S prime is strictly greater than cardinality of S prime. Okay. Okay, so let's see how it is. So, we have this S, we have picked some component C. We are saying that okay, let's pick one vertex V, and this is my new C prime. This is my C prime, and now there exists some subset, okay, some subset of C prime which fails Tutt's condition. Okay, I have something like this. So, let's revise our set again. So, let's sum T. So, earlier we had this, we were looking at this S. So, now what we do is like, let's move this V inside S and this S prime set as well, because this is also failing Tutt's condition. So, I am just pushing this S prime also inside this S. So, my T is, let us S union S prime union this vertex set V. Okay. Let us look at the measure of this, Qg minus T minus cardinality of T. I want to look at this. Okay. But first look at this set S prime. So, what we had? We have that Qg C minus S, cardinality of Q of C prime minus S prime is at least strictly greater than cardinality of S prime. Okay, that is what we have. Okay. So, if we want to look at write it as equality, what we will write? So, we write this, but there is, we can refine this actually. Let us look at this set C prime S prime. Let S prime is odd. Oh, yeah, plus 1, sorry. Okay, so let S prime is odd. Cardinality of S prime is odd. Then can we say something about the Q C prime minus S prime? We had this odd component. I just want to refine this inequality. So, I am saying okay, let us look at this closely and see what we can do. Okay. So, now we have proved earlier that every component is odd component. We are removing this v. So, now C prime is even, right. So, note that cardinality of C prime is even, right. So, now if you have that cardinality of S prime is even, then what can you say about this number of odd components in C prime minus S prime? Total number of vertices are even. So, can we have odd number of odd components? Because it will sum up to some odd number, right. So, if cardinality of S is even, then this number of odd component should be even, right. So, this is also even. What if cardinality of S is odd? Now, this S prime is odd, you have some odd components, then how many odd components we can have? Odd number, right, because if we have even odd component, then we are summing up to even and this odd, but C is even actually, C prime is even actually. So, Q C prime minus S prime is odd. So, that means either both are even or both are odd. Is this okay for everyone? This is little like okay. So, if we have this, that if both are even or both are odd and we have strict inequality, then if we want to write it as equality, then what could be the difference between these two numbers? This difference cannot be 1, right. This difference cannot be 1. This difference will be at least 2, right. So, that is why it will be at least S prime plus 2. Okay. So, from here this implies that the difference between these two is even, and so Q C prime minus S prime is at least S prime plus 2, or I can write minus S prime is at least 2, and this is d of S prime, right. So, d of S prime is at least 2. This I proved. Okay. Let us go back to the measure of T. Okay. So, this is the odd number of odd components. Can you give please 10 more minutes? You don't have any classes, right?
Yeah, I need to go. I'll watch it on YouTube.
Okay, okay, sure. Or you can ask doubts in the group if you have. Okay, so let us look at this set. So, this is the number of odd components in G minus T, right. Okay, so number of odd components. Earlier we proved that every component is odd, right. Every component was odd. So, this is Qg minus S. Earlier every component was odd. Now, one odd component, from one odd component I did something, right. I put this vertex V inside S, I put this S prime inside here, and by doing that, by removing these set and vertices putting in S, I may created some new components, right. I created some new components, these. So, how many new odd components I have like introduced now by putting this S prime inside? So, what I had earlier, I proved that every component in G minus S is odd. Okay. Now, in one of the component one of the odd component, I have done some changes. Okay. So, earlier and all the other odd components remained same. Okay. Now, in this one component, because I have put this V in S, I have included this S prime here. So, I may like introduce some new components, right. After removing this S prime and V, this C may have introduced many new components, right. So, how many odd components, but I have introduced, that is Q C prime minus S prime. So, I am saying that yes, because we proved earlier that every component is odd. So, this C was also odd.
So you remove V, it becomes even. Now you have S.
But it becomes even, and then I have removed this S prime also. I said okay, this C prime has even cardinality, but it has no one factor. I assumed that because it has no one factor. So, there exists some subset of C prime which fails Stutz condition. I said okay, this S prime is that set which fails Stutz condition. Fails Stutz condition means that number of odd components creating by removing S prime from this component is more than the cardinality of S prime, right. So, these many new odd components we have introduced, right. So, now in my T, because I am including this S prime here, so all those components are now in my G minus T.
The total number of new introduced are the first which are already present, Q G minus S plus Q C prime minus.
Yes, exactly. That is my point, that we have introduced these many new odd components and this were like already there, and minus, and this is like at least this is equal. Okay. This is equal, and cardinality of T is cardinality of S plus cardinality of S prime plus 1. Then this together we can take, and this will give me ds, and this together we can take, and what it gives me, QC. This is ds prime, so plus ds prime minus 1. Here also there will be one less, because this C one odd component I took, and from there I am doing something. So, Qg minus S minus 1 actually. So, this is minus 2 and this is ds prime. We earlier proved that ds prime is at least 2. So, this is at least 2, this is at least 2. So, this is at least ds. So, dt is at least ds, but cardinality of T is much larger than cardinality of S, right. So, again we got this contradiction. Is it okay with everyone? I think not okay with anyone.
Choice of S.
Hmm?
I didn't understand this contradiction at the last. So
Because we found some set which has greater D measure, at least that much D measure, and cardinality of T is greater than S, right. Let us write, and cardinality of T is strictly greater than cardinality of S. Now, this is a contradiction, right. Okay. So, please read this from the book, and if you have any doubts, then you can ask in group, WhatsApp group.
So this is a much more stronger characterization than that.
Yes, this is much more stronger, because here now you can see that if you have such set, you can actually give one factor, right. What we did in the reverse direction, we just showed that okay, because every component is one critical. So, you can just match one vertex from S and remaining has one factor by this property of S. So, only to find this such set is enough to give you a perfect matching, right. So, this
theorem implies Stutz theorem.
this theorem implies Tutt's theorem? Yes, yes. Like from the one direction itself, from these two, yes, because we are taking these two condition, and this will give me Tutt's condition actually.
But is this the original proof, because we are using Tutt's theorem?
Yeah.
We are using Tutt's theorem in this proof.
Yeah, but okay, so we have first proved that, and now we are using, so it is okay, I guess.
But it is then in a loop.
Then it's a
It is in a loop, like it is referring to the, it is like.
But we have proved that theorem, right? So we can use a weaker result if we have proved already.
But like independently, if this theorem implies Tutt's theorem, then they should not use Tutt's theorem.
makes sense.
Okay, so for that also you can use like induction.
Another proof.
Maybe you can use induction where, so in the first part we were not using, we were,
We can check the years it proved, so then we can understand that there might be some other proof for this before that.
no, actually you can use actually induction. Even in the book induction is given, that you can take the induction on the cardinality of G, and so okay, in the base case you can assume that okay, cardinality of G is 0, so automatically it holds. And then we take, so we are using strong induction, and we are saying that okay, if now currently the cardinality of G is n, then for smaller of any graph with this cardinality with order less than n, your theorem holds. Okay. And so here where we use Tutt's condition, there we can say that our theorem because holds now for smaller graph, because where we use Tutt's condition, I think in C, when we are looking at one component and doing something that okay, in where we said that okay, it is not one factor critical, so we are removing one vertex and the remaining component is not one like it has no one factor. There we use Tutt's condition, right. So this is a smaller graph. So now here we can say that okay, by induction hypothesis my theorem holds, and because my theorem implies Tutt's condition, so I can use Tutt's condition, right. So first you have to show that okay, this theorem implies Tutt's condition, right.
But doing the forward direction, we use the whole Tutt's theorem.
What?
Last step.
So in the forward direction, what we use?
Use the Tutt's theorem.
Yes.
Get that.
We said okay, G has one factor.
In fact,
It's okay, like you just don't use that Tutt's condition is there. You can just assume what the argument was there in Tutt's condition, that you have, because one factor, you have this set S, you have this odd components, then number of odd components cannot be more than cardinality of S, right. So forget about Tutt's condition, but you can give this argument that okay, cardinality of S cannot be less than the number of odd components, because in that case you won't be able to match those odd components to S, but you have one factor, right. So you argue in that way, don't use Tutt's condition, that is okay.
yeah, but
I think we should check.
there are like three places or 4 places.
So everywhere actually we are looking at a subgraph, we are doing something in some component, wherever we were using Tutt's condition. In the forward direction, we can use this fact that we can show actually that this inequality, that Qg minus S should be at least at most, what is this, yeah. So this we can argue differently, that to able to match every odd component with S, you need this condition. So we are not using Tutt's condition, and at every other place we are dealing with some component. So we are in some subgraph, in a smaller graph actually, and so by induction hypothesis you can use that your theorem holds, and so Tutt's condition holds. Okay. So you can do inductively. I thought it is easier, so that's why I used like Tutt's condition, but okay.
So the induction proof is there in the book.
Yes. That's the only difference, that you are starting with some G and you are saying okay, base case is true because it is 0, and then you are assuming that okay, now cardinality is n, and for every graph with a smaller order your theorem holds. We are using a strong induction, and then everything is same, but only in place of Tutt's condition we just can say okay, we are in a smaller graph, so our theorem holds. That's all.